I see HalvingGridSearchCV as a smart way to find the best settings for a support vector machine, SVM. It's like a tournament where we systematically eliminate underperforming models to find the champion. We're working with a dataset containing 1,000 examples. These examples will be used to train and test our SVM models. In our SVM, C and gamma are important tuning knobs that control the model's behavior. We are going to experiment with many different values for these. It is like trying various recipes to find the best cake. This parameter is crucial in controlling the efficiency of the search. A factor of 2 means that after each round of testing, I only keep the top half of the best performing models. This setting tells the algorithm to use all available computer cores, speeding up the search significantly. Imagine having many chefs working on different parts of the recipe simultaneously. Instead of using the entire dataset right away, I'll start with a smaller subset to quickly eliminate badly performing model configurations and reduce computation time. This is a more efficient approach than evaluating every configuration using the full dataset. In each round, the number of models I'm evaluating gets halved, as dictated by the factor. I keep iterating, improving my model until I have a champion. This is the heart of the algorithm. I evaluate models, toss out the weak ones, and repeat the process until I have only a few left. It is like a tournament, where I keep discarding the losing teams and only the best teams survive. The final model is the one that performed best across the iterations, not necessarily on the entire dataset initially. This process selects a model efficient in terms of computing resources and time. The first round of testing evaluates all the hyperparameter combinations, but only on a subset of the data, not the full 1,000 sample dataset. I see the parameter n_jobs equals -1 . This tells me that HalvingGridSearchCV will use all available CPU cores to speed up the hyperparameter search. That's great for faster results. The factor equals 2 setting means we evaluate half the number of models in each iteration after the first one. For example, if you start with 100 models, iteration 2 would evaluate 50, iteration 3 would evaluate 25, and so on. It's a clever way to efficiently narrow down the search space. The algorithm selects the final model based on its performance during the successive halving. It's not necessarily the best model on the entire dataset initially, but the best one among those that made it to the final iteration. It might even be retrained on the full dataset after selection, but that's not guaranteed here. Think of it like a tournament, only the top performers advance to the next round. This is the last round of the hyperparameter search. After discarding poorly performing models in previous iterations, the best remaining models are evaluated, and a winner is selected. I'll explain how HalvingGridSearchCV works. It's a clever way to find the best settings, hyperparameters, for a machine learning model by trying many different settings and progressively eliminating the worst performers. It's like a tournament where only the best get to the next round. In the first round, HalvingGridSearchCV tests all the hyperparameter combinations of provided, but only on a small part of the dataset. This is a smart move because it quickly weeds out the really bad combinations without wasting time on the whole dataset. That means that after each round, only the top half of the best performing models move on to the next round. Think of it like cutting the field in half after each game. After the first round, each subsequent round uses the surviving, top-performing models. HalvingGridSearchCV then tests these on a larger portion of the dataset. It continues this process until only a single model remains, the best of the best. Tells the algorithm to use all available computer processing power to do the work in parallel. It's like having a team of people all working on different parts of the problem at once, making it much faster. Finally, HalvingGridSearchCV chooses the model that performed best across all rounds, not necessarily the model that performed best on the whole dataset at once. It's a champion selected through a series of competitions, not just one final match. I'm working with a dataset containing 1,000 samples. This is the data HalvingGridSearchCV will use to find the best hyperparameters for my model. In the first round, every possible combination of the hyperparameters C and GAMMA for the SVM, support vector machine model is tested. I select only a subset of the data at the start because testing all combinations on the whole dataset right away would be very slow. This means I have the number of models I test in each round of the search. It's like a tournament, where only the top half of the players advance to the next round. In the first round, I test all the possible combinations of my SVM's C and gamma parameters. But I don't use the entire dataset. I use only a subset to speed things up. These are all the different settings for C and gamma that I want to try to optimize the SVM classifier. It's like trying different recipes. Some will work better than others. To make things efficient, I don't test all combinations on the entire dataset. Instead, I use a smaller portion of the data in the initial iteration. After each iteration, I only keep the top performing half of the models from the previous round. This iterative process is called successive halving, meaning that the number of models is getting halved at each step. This tells my computer to use all of its processing power. Think of it as having lots of helpers all working at once to get the results quickly. At the end of all iterations, the final model is the best performer from among those which survived successive halving. It is not necessarily trained on the entire dataset initially, that depends on the underlying CV parameter. I see HalvingGridSearchCV as a clever search strategy. It's like a tournament where you start with many competing models, different combinations of hyperparameters, and repeatedly eliminate the weaker ones until you find a champion. The halving part means you cut the number of competitors in half after each round. After the first round, I have the number of models. Only the top performing half of the previous round move to the next. This continues until I'm left with the best performing model. It's an efficient way to narrow down the search space. It's like gradually zooming in on the best area of a map. This parameter controls the halving part directly. A factor of 2 means I eliminate half the competitors after each round. If I set it to 3, I'd eliminate 2/3. It's a crucial knob for adjusting the aggressiveness of the search. n_jobs equals -1 is a simple, powerful command. It tells the computer to use all its available processing cores. This massively speeds up the search process because I run multiple model evaluations simultaneously. Think of it like having many workers collaborate on the job. In the first round, I evaluate all possible hyperparameter combinations, but not on the entire dataset. I use a smaller sample to get a quick idea of which combinations are promising. This is an important step that helps prevent wasting resources on poor choices. The final model is the one that emerged victorious at the end of the tournament. It's the best performing model after all the successive halving rounds. However, this doesn't necessarily mean that it's trained on the entire dataset. That depends on other settings I might use. I have 1,000 data samples to train and evaluate my models. This is my data pool for the entire process. These are settings, hyperparameters, of my support vector machine, SVM, classifier that I want to optimize. C and gamma control the model's behavior, and I'm exploring a grid of possible values to find the best ones. I see HalvingGridSearchCV as a clever algorithm for efficiently searching the best hyperparameters for a machine learning model, like an SVM. It does this by cleverly reducing the number of models you need to test. It's like a tournament where the worst performing models are eliminated in each round. In the very first round, I evaluate all the possible combinations of C and gamma hyperparameters on a smaller portion of the dataset. This is a sneaky way to quickly get rid of obviously bad combinations without wasting time on the whole dataset. Instead of using the entire 1,000 samples right away, I start by using just a small part of it. I do this so I can efficiently evaluate many hyperparameter combinations quickly. After each model evaluates on a subset of data, I check its performance. This tells me which models are doing well and which are not. I use this information to eliminate bad models. The n_jobs equals -1 parameter tells the algorithm to use every available processing core on the computer. Think of it like having multiple chefs working on different parts of the meal at the same time, faster results. The factor equals 2 parameter means that after each round of evaluation, I keep only half of the top performing models. This is my halving strategy. It's like cutting the field of competition in half after each round. After the initial round, I keep running more rounds. But in each new round, I use a larger portion of the dataset and test only the best performing models from the last round, eliminating about half of the candidates each time. After all the iterations are complete, I pick the single model that performed best across all the rounds. I'm picking the winner from the tournament. The final model is the one that was consistently among the top performers throughout the successive rounds. It may or may not be trained on the entire dataset, depending on the underlying cross-validation strategy. I'm trying to find the optimal settings for the support vector machine. The hyperparameter grid, in this case, represents a set of C and gamma values that I am testing. It's like exploring different recipe ingredients to see what tastes best. I have a dataset with 1,000 different examples to train my model on. Each example helps me learn more. I have a dataset with 1,000 data points. This is the data that I will use to train and evaluate my support vector machine, SVM, model. In the first step, I evaluate all the different combinations of the SVM's hyperparameters, C and gamma, ONASMALLPART of the entire dataset. I don't use the whole dataset at once because it's more efficient to find good hyperparameter combinations faster by working on a subset initially. After several iterations of testing different hyperparameter combinations, I choose the combination that performed the best across all iterations. It's not necessarily the one that worked best on the entire dataset directly because of the way I narrowed down the options. I'm tuning two parameters in the SVM, C, which controls the penalty for misclassifications, and gamma, which controls the influence of each data point. I'll try various combinations of C and gamma values to find what works best. I'm using HalvingGridSearchCV, which is a scikit-learn algorithm that helps find the best hyperparameters for an SVM classifier using a clever method to reduce the number of tests required. The backquote factor equals 2 backquote setting means that in each iteration, I keep only half of the best performing hyperparameter combinations from the previous iteration. Tells the algorithm to use all available CPU cores, parallel processing, to speed things up. By using backquote n_jobs equals -1 backquote, I make the most of my computer's processing power. This speeds up the hyperparameter search considerably. Finally, I select the model that achieved the best performance after many iterations of testing and pruning out poor performing models.